Okay, so again, we're working on section 9.1, correlation and regression. The talk today is a bit complicated because I try to explain where all of the formulas come from and what they mean. It's a little stiff, but in the end, we're going to use Desmos to do all the computations. So this is actually pretty easy. It's just important to understand some of the more subtle concepts. Okay, so again, it's on correlation and regression. Okay, this is gonna take probably an hour and a half to get through, and we just have an hour and a half. So let's see if I can pull it off. All right, so section 9.1, in this lesson, we're looking for rules that describe relationships between two quantitative variables. This is chapter 9 and chapter 10, where we look for relationships between variables. In chapter 9, they're quantitative variables, and in chapter 10, they're categorical variables. So either way, we want to be able to describe when one variable can be used one variable is influencing another, okay? Or that maybe more accurately, a relationship between two variables means you can use the outcome of one variable to predict the outcome of the other variable. So whatever that means, you'll see it in an example here. So we've got these organizations that compile data for 8 different cities in the table below here. The variable X represents the number of registered automatic weapons in thousands in a given city. And what you have 1, 2, 3, 4, 5, 6, 7, 8. There's 8 cities here. And so for each city, there's the number of registered automatic weapons, again, in thousands. And Y represents the murder rate in that city. And now a murder rate is typically given in the number of murders per 100,000. So it's not a percentage, it's per 100,000, okay? Now, the first thing we do to determine if there's a relationship between two variables is we like to have some sort of graphical depiction of the outcomes of the data that you gathered, and that will often tell us something about the relationship between the variables. So I've rounded these all to whole numbers just to make this as simple as possible. So let's go ahead and make our scatter plot. First point is 3, 5. Sorry, that's the last point. I'm going from the bottom. Second to last, 2, 4. Then 3, 7. Then 7, 12. Then 1, 4. Uh-oh. Yeah, then 4, 10, then 8, 11, and then 12, 13, like that. Okay, so again, X is the registered automatic weapons, Y is the murder rate. Now, again, this is not a statistical study. So this is not an experiment, an experimental study. It is statistical though. In experimental studies, you can make statements of cause and effect that this is causing that, but that's not happening here. This is just an observational study where we observe. Sometimes we say there are relationships, but we don't try to say that one is causing another thing. So what do you guys think you see in these data, being very careful not to make a statement of cause and effect? Anybody?
They look maybe linearly dependent.
But tell me about guns, and they do, Dan. Yes, I agree. But tell me about guns and murders.
There's a correlation between the number of guns and the number of murders.
Meaning if one city has more guns, what does that mean?
If one city has more guns, it has more murders.
Okay, so does that mean if we took guns out of cities, that the murder rate would go down?
Not necessarily. Just
Because
means if we find guns in cities, we are also likely to find murders there.
right, good. And removing guns, if you think that would make the murder rate go down, then you're thinking cause and effect. And this is not cause and effect. And I like to turn these around so that, yes, we do see that cities with more guns do have higher murder rates, but I think a lot of times people buy guns to protect themselves because the murder rates are high. So you can't say that more guns is the cause of more murders. It may be that more murders is the cause of more guns. And of course, these are sort of negative feedback loops. If you think about it, one bad thing reinforcing another, reinforcing the first. So it's too messy to talk about cause and effect here, but we do see a relationship. So the question is there a way to sort of come up with some mathematical tool for describing the relationship? And of course, we're going to find what's called a line of best fit here. The goal is to find an equation of a line that sort of goes through the middle of that, and then have a measure for how good it works. Okay. Any questions? Okay, so I think we got a pretty good description. The relationship between these variables is what we're going to call positive. Okay, what that means is as x increases, increases, y tends to increase with it. Not always. Okay, but you can have negative relationships as well. There's a handful of positive relationships that are graphed here. Now, we're going to talk about weak relationships and strong relationships. The strong relationships are ones where you can make really good predictions of y for a given value of x. Which one do you think would give the best predictions? Anybody? A, B, or C? 1, 2, or 3?
3.
Yeah, the third one would give the best. So if I give you a value of x, you would go up to this nice, tidy little pattern here and pick a y value somewhere in this circle that I drew. Okay, that's a good prediction, and it will have a small margin for error. Okay, the strength of the relationship is just simply how good your predictions should be. Okay, so when you try to do the same thing with the first one, you pick an x value and you go up and you say, well, what are my possible y values? And you see how much margin for error I'd have to allow for that one. I can still make a prediction. I'd go to the middle. Okay, but I'm going to have this huge margin for error on the first graph. The second one's better. The third is best. When the relationship goes uphill as you move to the right, we call them positive relationships. So as x increases, y tends to increase as well. Those are positive relationships. So let's go ahead and describe verbally what these are. This first one is a weak positive relationship. Second one is a moderate positive relationship. Okay, and the last one's quite strong. This is a strong positive relationship. Those are the ones
At
that make
what,
best predictions. Sorry?
at what point do we say a weak positive relationship is no relationship?
I'm not ready to answer the question, but I will before it's all over.
Okay.
And by the way, weak. Oh, you're asking me the difference between weak and none?
Yes.
Yeah, I think for all intents and purposes, weak and none would be considered none. Meaning,
Got it.
it's sort of like if you don't have proof that you've got some good, that there's, it's like a hypothesis test. If you can't
Right, it's
prove
like
it,
accepting the null.
yeah, if you don't have strong evidence, then just forget about it, right?
Right.
So, I mean, this weak relationship could be anything. It's going to be positive, but it's not going to be useful. And the margins of error are almost as big as the predictions you'd make. So it's just pointless, right? So anyway, we go on. I just wanted to do some graphs of negative relationships. So these are ones where one variable increases, but the other tends to decrease. Okay, so let's put that in parentheses here as one variable increases, the other tends to decrease. And so you just think about things that sort of degrade. Like my IQ tends to go down as my age goes up, stuff like that. Okay, so the first one.
That might be nonlinear.
Hard to say. I hope it won't go negative at any point like this one does over here. So the first one's a weak negative relationship, sort of goes downhill. I don't know if you can see that. And we do have rules for how we distinguish, like moderate from strong. They're sort of arbitrary rules, but they're typical. So strong. Any questions, anybody? Okay, so let me, I'm gonna just clean up a little here. It's hard to read. So. Okay, so this is actually a science project that my kid did like in 8th grade. And you could tell he's a nerdy child of a nerdy dad. But what we were doing here in his science project was we were making batteries, and the pH is the pH of what they call the electrolyte, which is the liquid in the battery. And then we were just measuring how much electric current would come out of the battery. And a pH of 7 is neutral, so that's neither acid nor alkaline. And so you get the worst batteries when your electrolyte is as a neutral pH. But if you go acidic, the electric current went up. But if you go, what do they call alkaline, then the current goes up as well. So you can have acid batteries or alkaline batteries. Alkaline is the opposite of an acid, basically. And so that was a non-linear relationship, pretty strong non-linear relationship. But it's still a relationship, meaning you can still use one variable. If you tell me the pH of the electrolyte, I can kind of give you a prediction of what the electric current out of that battery would be. Okay, any questions about that? It's more complicated than what I'm saying. I'm sorry, I just screwed up.
What was your electrolyte?
Well, it just depended. The neutral ones were things like milk. if you want a very strong alkaline, you can use, we used ammonia, which has like a pH, ammonia is like a pH of, I think it's 11 or 12. It's really strong. It's nasty stuff, but for the acids, we started with lemon juice, and I think we actually went and bought some muriatic acid from the hardware store, which I had a bottle of muriatic acid in my garage. It's probably still sitting there now, and I kind of was like, why did I do that? Why did I do that? There are also relationships that don't exist between variables. So this was, I should not have let this honors student do this. I gave a lot of you guys a hard time. It's like, yeah, no, you shouldn't do that one. This one I shouldn't have let him do, but he did. He was looking for a correlation between how much sleep students get and their shoe size. And so it's no surprise we don't see an uphill or downhill. We don't see anything here. So, but that's an important case and I'm using his data set forever. So lovely. Okay, so this lesson, we're talking about linear relationships, and that's all we study in this intro course. More advanced courses will do nonlinear relationships and also relationships where there's more than one input variable. So this can be super, super complicated. We're just going to do the simplest case in this class. So we want to learn about linear relationships. The first thing we'd like to accomplish is to find the equation of what we call the line of best fit. Also, this is known as the regression line. It's called the regression line of something to do with Nazis. Okay, and that's a little bomb I dropped, and I'm going to let it go. When I say Nazis, it all started with this thing called eugenics, which is not that many steps away from atrocities like ethnic cleansing and whatnot. So the term regression in regression line, everybody just calls it a regression line, but it goes back to some pretty dark history in Europe. Okay, so here's the equation of the line of best fit. We're going to use a hat on the y coordinate to indicate that it's a predicted y coordinate, not a real y coordinate. If you go back to the original table, the y values are the observed murder rates. They're not predicted murder rates. So we distinguish the predictions from the observations by putting a hat on the y value so everybody understands. Okay, it's not a real city. The slope of the line is b, that's the number that gets multiplied by x, and the y-intercept is a, that's just this constant without a variable. We use y hat for points on the line because y is used for actual data points, which typically are not going to be on the line. Before we can define a line of best fit, we need to label a few quantities that measure fit. What does it mean to have a line of best fit? The vertical distance from a point, xy, to the line is the difference between the y coordinates. Okay, this is called the residual or error. Residual is a more accurate term, but error is easier to understand. Okay, so the y value is the observed value. The y hat value is the predicted value for y. Okay, and this is for a given x. Okay. And the difference between what you actually observe and what you're predicting is residual. Okay. And again, you can think of that as an error. The line of best fit should minimize all of the residuals. We want our total error to be as small as possible. It says to label a residual for 1 point on the graph below. Well, maybe I'm trying to find a good one here. I think I'll just say this point right here would be xy. Okay. The point on the line of best fit is where you're going to get your prediction from. So it has the same x coordinate, but because it's a predicted y value, you would call that y hat. And actually, I'm going to label that with a little x. I don't want to confuse that with the real data points. Okay. And then the residual is just the distance between the real data point and the prediction. So this distance here is what we call residual, or just error. Okay, any questions? Now, again, we want to pick a line where the points are as close as possible to the line. But my goal, therefore, is to minimize these residuals somehow. Okay. But there's a lot of them, so I'm going to have to sort of minimize the total of all the residuals, if that makes sense. I don't want to just minimize one residual. If I only want to minimize one residual, I'll make the line go through that point. Okay, but if I'm trying to minimize all of them, I'm going to have to think about how do I combine these residuals into one big measure of error, total error. That's what I'm trying to minimize. Okay, so the deviation from the line of best fit, which is the regression line, to the mean line, that's in blue. Okay, so this is the mean of Y values. Okay. It says the deviation from the line of best fit to the mean line is Y hat minus Y bar. Okay. So that's going to be another distance, which I think I'll do in purple. It's going to be hideous. Okay, so this distance right here is Y hat minus Y bar. The mean of Y values is Y bar. Again, the residual is Y minus Y hat. Okay. It says the total deviation, I'm now down here, the total deviation from the point XY to the mean line is Y minus Y bar. It says to label this distance on the graph. So now I've got to figure out how I'm going to squeeze this in. I think I'll do it off to the right. So this is going to be my total distance from the point to the mean value of Y. So this is total, what I'll call deviation, which is Y minus Y bar. That's what you average when you compute a standard deviation. When they say standard deviation, they mean the standard deviation from the mean. Okay. Okay, so I've labeled that. So I'll read this again here. It says a residual is the distances from each point to the line, and we want to minimize all the residuals. How should we minimize them all together? Is the question. Okay, so these numbers, these residuals are what we're trying to minimize. Well, here comes. It turns out we can't minimize the sum of the residuals because they always add up to 0. Now, this was the same problem we had when we were computing standard deviation. The sum of deviations from the mean, if you want to average them, the sum of the deviations from the mean, they always add up to 0. And that's where that whole notion of degrees of freedom came from. There were n deviations, but only n minus 1 of them were free. So that was the degrees of freedom. We have the same thing with residuals. They will always add up to 0. And so that makes it difficult. Again, if this is the line of best fit, some of the deviations are going to be below the mean, or sorry, below the line of best fit. So those residuals are negative. Some of the residuals are points above the line of best fit. So those are positive residuals. When you add them up, you get 0. Okay, always. So
and only, right? Like did they only add up to 0 when it is the line of best fit?
That is true. That is true. So there's maybe a little bit of circular logic here, but I'm not going to address that. Okay, so what we did with standard deviation when the deviations always add up to 0 is we squared them and then averaged and then take the square root. So we're going to do the same. We're going to solve the problem the same way. Statistics always solves that problem by not summing the values, but summing their squares. And so we'll go ahead and continue. It says, they always add up to 0. Thus, just as variation from the mean is summarized with sums of squared deviations in the standard deviation, we'll summarize total deviation from the line of best fit with the sum of the squared residuals or errors. The sum of squared residuals or errors is denoted SSE, that's sum of squared errors, okay? It measures the variation in Y that's unexplained from the line of best fit. So we call this unexplained. I'll put this on the graph. I hope it may be on others as well. The residual is unexplained because we don't know why it's not on the line. Also, because the explanatory variable is not predicting it. The explained part is what the explanatory variable does predict. That's the Y hat value. Okay, so the residual is the unexplained deviation. Okay, we'll talk about that more as we go. We're going to use a bit of algebra to minimize the sum of the squared residuals. That's our goal. These errors, these residuals need to be made as small as possible altogether. Okay, how do you measure that they're small altogether? You can't add them, but you can add their squares and use that to measure how close they are to the line. Okay, so it says we're going to use a bit of algebra to minimize it. This will yield the slope and the y-intercept of the line of best fit. Okay, so the algebra is simplified if we first take z-scores of each x and y value. The z-score of an x value will be denoted z sub x. The z-score of a y value will be denoted z sub y. So with these, the firearms data, it wants us to give the statistics below. So you can see we need to compute x bar, y bar, sx, sy, etc. So I'm going to pop over to Desmos and remind you how this works.
Professor, quick question.
Yeah.
So, do we also have chapter 9 on the test?
No.
No? Okay.
Thanks for asking. It's just through chapter 8. Okay, so I guess I'll call the first list X with a capital X. And so we'll just type X equals, and then remember square brackets to hold them. So 12, 8, 4. Could somebody do the Y's? I worked really hard for these to come out sort of nice with my very creative rounding. So the mean is just 5 for X. Can we get the mean of the Y's?
I got 8.20.
Could you repeat that?
8.25.
8.25. And then did you get the standard deviation? I want 4 places after the decimal, if you don't mind.
Yeah. It's 3.6936.
Fantastic, thank you. Any questions? Okay, so now we need to do some z-scores. So you can see all the z-scores, but one zx and one zy are done. So for x equals 4, zx should be x minus x bar over the standard deviation of x. So this would be 4 minus 5 over the standard deviation, which was 3.7033. Okay, so that's like -1 over 3.7033. So I got -0.2700 for x. That sounds about right. Anybody, could somebody do the y? Okay, well then I got 0.4738, I guess. Now they're going to ask us to graph this. Okay, this is in the ZX, ZY plane. So I'll just think I'll round these all to the nearest 10th in my head. So on the first point, ZX is 1.9, I think, and ZY is 1.3. So I'm just thinking 1.9 and 1.3 is going to be something like maybe here. Okay, that's the first one. Next one is 0.8 and 0.75, I guess. So 0.8, 0.75 back here, I think. Got it. Then negative 0.27 and 0.47. So negative a quarter basically, and then a half. So that's going to be right. Oops. Right about here. Okay, so I got that one. Now negative 1.08 and negative 1.15. That maybe. Then 0.5 and 1 basically. 0.54 and 1.01. So maybe just right there. And then negative 0.54 and negative a third basically. Maybe here-ish. negative 0.8 and negative 1.15. So I'll put that like right here, I think. I think this is a mistake. Is that a negative up there? I have to check something. No, it's okay. Okay, and then so I got that one. There's only one more. Negative 0.54 and negative 0.87, so that's close to 0.9. So maybe there. Okay. So any questions about the graph? You're not going to, by the way, this is just development. You're not going to do anything like this on any exam, but I want you to understand where things come from. Now, one of the things I want to do, I hope it's asking, oh, no, it's not. So one of the things I want to do is to compare this with the original graph. So I wonder if I could do a screenshot. I don't remember how to do that. So what I think I will do is just go to my original scatter plot that we did. And I'm just going to copy the points and just show you that the distribution, when you take z-scores, it preserves the distribution. So here's the original graph. You see? It's a little spread out differently, but it's an identical distribution of points. So the idea is that the line of best fit in this thing I call the ZX, ZY plane is going to be situated exactly as it would be among these points in the XY plane. Okay, any questions about that? So taking z-scores does not affect the distribution of the points. We still have the same geometry, so it makes sense to find the line of best fit here. One of the reasons why it makes sense to find the line of best fit in this plane is that, first of all, that the mean of z-scores is always 0, as you can see in this little statement here. So there's a list of facts here. So the mean of any collection of z-scores. So you're doing the sum of z, which is x minus x bar over n, and then that whole thing is divided by n. Okay. And you factor that n out, so you have a 1 over n over another n, which becomes a 1 over n squared. And then this is just the sum of x minus x bar. And I won't go through the trouble. We know that the sum of deviations from the mean is always 0. You can go through the math on this if you want, but I won't do it right here. Okay, so this whole thing just wipes out to a 0. Okay, so z-scores always add up to 0 when you add up a full set of them. Okay, so now it's talking about the line of best fit, but it's going to be in the ZX ZY plane. Okay, so here comes the line of best fit in the ZX ZY plane is going to be z-score of y hat equals r. That's going to be the slope times the z-score of x plus a y-intercept, which is k. The slope is r. The intercept is k, and it's not hard to show that k will be 0. I'm not going to do that. So we're going to go ahead and just say that with k always 0, that means the line of best fit will always go through the origin. So that's an intercept. And what we're saying is that the z-intercept, or sorry, the zy-intercept is always going to be 0. So wherever this line of best fit is, it's going to go through the origin. And that's one of the main reasons why we do this in the ZX, ZY plane, because now we only have to find the slope. Okay, I think in the book, I actually show that it has to go through the origin, but that takes a little bit too long, so I'm not going to bother with that here. There's a little more ugly work we have to do here. So we've got the line of best fit. It says label a point zx, zy, its residual zy minus zy hat. The deviation from the best line to the mean line and the total deviation. So this, they want us to do this up here. So let me do a line of best fit here. I drew one and then I took it away. Now I'm putting it back. And it needs to go through the origin. Okay, so let me see here. This point, I guess, is the one we were working with. I think that's too steep. So forgive me while I continue to fiddle with this. So I kind of like that better. If I could just get it to sit. All right, so this is the point right here we're going to call zx, zy. This point, if you go straight down to the line of best fit, you're talking about a residual. So right here, straight down to this point, that's going to be zx, sorry, zx is the same, but this is going to be the z-score of y hat because it's on the line of best fit. Like that. Okay, and then let me see what else they want. Label the residual. Okay, easy. So the residual is this distance. Sorry about the purple. Nothing against purple. Okay, so this is residual. This is zy minus the z-score on the line of best fit, which is zy hat. Okay, any questions? Just got to find the equation of that line. Okay, so maybe I'll label the line real quick here. So that line, remember, is z y hat equals r times z x plus the y-intercept k, but k is going to be 0. R is the slope. Okay. So the k equals 0 is the y-intercept or the zy intercept. So k equals 0. That's saying that the line goes through the origin. Okay. I'm sliding on. You guys okay? Should I pause here? All right. Okay, so there's a couple of algebra things I need to straighten out. It says first we want to find the relationship between the difference of two y coordinates and the difference between their z-scores. So they're taking the z-score of y1 here and the z-score of y2, just arbitrary y coordinates, y1 and y2, whatever they are. And what I'm going to do is put in a formula here. So the z-score of y1 would be y1 minus y bar over sy, standard deviation of y. Minus, that's the z-score of y1. Now the z-score of y2 is y2 minus y bar over the standard deviation of the y coordinates. You can actually put these together. So you'd have y1 minus y bar minus y2. And then there's a double negative here. So that becomes a positive. So it's plus y bar. And you see the y bars cancel. That's kind of what we're trying to get out of that over a single sy. And so you end up with just y1 minus y2 over sy. So that's the difference of the z coordinates is just the difference of the y coordinates over the standard deviation of y. And from that statement, you can say that y1 minus y2 is the standard deviation of y times the difference of the z coordinates, which are z y1 minus zy2. So there's that. And then what they do here is they square that. Okay, so if you square both sides of that equation, you get the standard deviation of y squared, which is the variance of y, times this square of the difference of the z-scores. So z y1 minus z of y2. Okay, so we're going to need this fact going forward. I'll use it 2 or 3 times or more. Okay, next, the sample standard. So this is just, we just put this in our toolbox. We're going to use it. Okay, so next, the sample standard deviation formula is something we've seen many times. If you square this, you get the formula for the variance. It says to rearrange this to determine the formula for the sum of z squares. So this is kind of crazy, but what you can do on this is you can multiply both sides by n minus 1, like that, and divide both sides by s squared. Just to show, and of course on the left, the n minus 1s, sorry, the s squares will cancel on the left. And the n minus 1s cancel on the right. And the point is that what you have on the right is the sum of z-scores. So if you look at it, it says n minus 1 is the sum. Everything's being squared, so I can put them together, of x minus x bar over s. I guess we could call that sx, but it doesn't matter right now. Okay, so this is the sum of z-scores squared. Turns out that it's always n minus 1. So if you have a full collection of z-scores, you just have a set, and you take all the z-scores. If you square them and add them up, you always get the sample size minus 1. Okay, so that's our, this is just a fact, and it's another tool we need in our toolkit. So add up all the z-scores squared, you will always get the number of them minus 1. So if it's 10 z-scores, you square them, you add them up, you'll get 9. Doesn't matter what the z-scores are, the squares will add up to 9. Okay, that's weird. Next, that's just another tool in our toolkit that we're going to use repeatedly. Next, I have to minimize the sum of the squared residuals. Squaring things is quadratic, so I'm going to kind of remind myself something back when I studied quadratics. Okay, so right now, this is a quadratic equation in 2 variables. I'm assuming a is positive here. And when you graph a parabola, it has a lowest point. And again, we're trying to find the minimum of a sum of squared errors, which is quadratic. Anytime you square things, it's quadratic. So I'm trying to find the minimum on a parabola. And what you learn in an algebra class, and a lot of you guys maybe remember, and some of you probably have forgotten, is that this point called the vertex, the lowest point on the parabola, is where x is negative b over 2a. So I'm going to put that mark down right there, negative b over 2a, and that finds the lowest y value. Oops. Okay. So that's another tool in our toolkit. I think those are all the tools we need. So I'll be going back and sort of referring to the 3 facts that we laid. Well, there were actually 4 facts. One was that the mean of z-scores is always 0. Okay, mostly because the sum of z-scores is always 0. Second, that if you square the difference between 2 y-coordinates, then that's the same as the square of the difference of the z-coordinates times the variance of the y-coordinates. Okay. Then the sum of z-score squared is always n minus 1. And finally, to minimize a point on a quadratic, which has equation y equals ax squared plus bx plus c, where a is positive, x has to be negative b over 2a. Okay, so now it's time to minimize the sum of squared errors. First thing I want to remember here is that this is a difference between 2 y-coordinates, and the difference is being squared. We talked about differences between y-coordinates, they're squared, and we said we can change it to something like this. Okay, so what I'm going to do is I'm going to say, okay, let's look at the sum of the difference of the y-coordinates squared, but let's change this to sy times the z-score of y minus the z-score of y hat. Okay, both of these are squared like that. I think I would bring the sy square out. So let's write this as sy square sum of the z-score of y minus the z-score of y hat squared. And then I'm going to square this thing. So I'm going to write sy squared. Oh, and let me go ahead and remind you, the z-score of y hat up here, way up in the graph, we said that the z-score of y hat is the equation of the line of best fit in that plane. K is 0, so z-score of y hat is just r times z-score of x. So I'm going to put that in here, make a little note. Z-score of y hat is just r times the z-score of x. Okay, so here goes. Rewrite this, oops, as the z-score of y minus r times the z-score of x. Square it. And now I am going to square this. So I'm going to have sy squared sum of, this is the first inner, outer, last thing is the FOIL method for squaring. So you square the first and you'll get a zy squared. The outer and the inner, they're going to be the same. So there'll be 2 of them. And it's going to have an r. You'll have the z-score of y times the z-score of x. And then I square the last, which is the rzx. It's negative, but when you square it, it will become positive. So you get r squared times zx squared. Okay, so that's just using the FOIL method to square a binomial. Now, this thing is actually a quadratic in R, but I'm gonna go ahead and recognize that when you do a sum like what I have here, that you can do the adding and subtracting here first, and then add those all up, or you can just compute these individually and then add them up one at a time. It just means it doesn't matter what order you add things in. So I'm going to add them in this order. I'm going to write sy squared and sum this way. I'm going to do the sum of my zy squares minus the sum. The R is a constant, so I'm going to factor that out of the sum. I'm going to put the 2R out front. That does not vary, but ZY and ZX do vary, so I have to add those up individually. So the sum of ZY times ZX. And finally, the R squared is again a constant, so I'll have R squared, but the ZX's will vary, so I have to add those up with the R squared factored out. So that's just a way of rearranging this algebraic expression to something equivalent. Now, what I want to do is show that this is a quadratic. So you could think of this first part is A. This second part, let me put the R in front so it's a little more clear. I'm going to move the R next to the minus sign and put the 2 after it, so that this next part here is going to be my B. It's actually going to be negative. And then my constant is this thing here. That's going to be C. So this is in quadratic form. The leading coefficient is positive. So let's write it this way. A is the sum of ZX squared. B is, no. Yeah, that's right. B is going to be -2 times the sum of ZY times ZX, or ZX times ZY, if you like. And C is the constant. So this would be sum of ZY squared. Okay, now there's a couple of things we want to pay attention to very carefully. First of all, we learned that the sum of ZX squared is the sum of a bunch of squared Z scores. We learned that that's always your sample size minus 1. So A is in -1. C is also in -1. I think there's a mistake in here somewhere. Let me just stare at this for a sec. No, I think we're okay. So the C is the sum of the ZY squares. I actually don't care about that right now. I believe it's also in -1, but there's something going on that I don't understand because this doesn't look familiar. Anyway, so I've got SY squared. The C is the n -1. Because it's again the sum of a bunch of Z scores squared and added up. That always adds up to the sample size -1. Okay, so then I have minus R times B, which is this mess, to sum of ZX, ZY. And then plus the R squared times A, which is an n -1 R squared. Okay, so this is minimized when the variable is -b/2a. So if you go back here, remember when you're working with something of parabolic form, or I should say quadratic form, where the leading coefficient is positive and ours is, then the lowest point is when the variable is -b/2a. What we're trying to find right now is our variable, the thing being squared, is r. So this is when r equals -b/2a. So the b, the negative b, is going to be +2 sum of ZX zy over, that's negative b, over 2a, that's 2 times n minus 1. Okay, the 2's cancel. Okay. So you've got that. We have determined the value for r. While I'm at it, I would like to say that the sum, just a note here, that the sum of zx, zy, if you multiply this n minus 1 over by the r, this just becomes n minus 1 times r. Okay, so this part right up here is what I want to say is going to be n minus 1 times r. Okay, and then let's see what we get here. So this is sy squared times, let's keep the parentheses for a little longer. You've got the n minus 1 minus r. I guess there's a 2r there, so let's put the 2 back. So 2r times an n minus 1 times r, and then plus an n minus 1 times r squared. I feel like I should factor n minus 1 out at this point because it's in all three terms. So I'm going to write an n minus 1, an sy squared, and then what's left after I factor out all these n minus 1s is when you factor n minus 1 away from itself, you just get a 1. So there's a 1 minus a 2r squared plus another r squared. So negative 2r squared plus 1r squared is negative r squared. So in the end, you get n minus 1 times sy squared times 1 minus r squared. So this is the minimum of this sum of squared errors. Then it occurs when the slope r is the sum of zx, zy over n minus 1. Yikes, so that's the formula for r, which is very closely related to the slope of the line of best fit. It is the slope in the zx, zy plane, but I need to move it into the xy plane. So that's where we're going next. So in the zx, zy plane, we said z-score of y hat is r times z-score of x. But I need to put that into the xy plane. So the z-score of y hat is just y hat minus y bar over standard deviation of y equals r, and we have the formula for r up above, times z-score of x, which is just x minus x bar over standard deviation of x. Okay. Now, it says to give the slope in the y-intercept. So I actually need to allow myself some more space than what I just gave. So I'm going to move this over because I did forget I have to do the slope in the xy plane. Okay, so I think what I'm going to do is multiply both sides by sy. So if you multiply by sy, you're going to get y hat. I think I did something. Hang on. No, it's okay. So y hat minus y bar is equal to, I'll have the multiplying by sy. So I think I'll put that outside here. So it's times sy and then sy times. Okay, so it'll go away there, but then I'll have the r times the sy. So r times sy over sx times x minus x bar. Okay, so this is what they call point slope form. Okay, this number in front of, and again, this is just an algebra thing. So if you remember algebra, you'll remember that the number in front of the difference of the x's is the slope. Okay, so the slope here is r times sy over sx. Okay, now to do the y-intercept, there's a couple ways to get it. You can make x 0, and that will work. That's how you did it in algebra. Or you can just put it into slope-intercept form, which is kind of what I want to do. So I'm going to add y bar to each side. I'm going to distribute this. So here's some more. I'm going to do y hat minus y bar distributing. I'm just going to use the word slope now. Okay, so equals slope. Times x minus x bar. Okay, so y hat minus y bar is equal to the slope times x minus the slope times x bar. And then I'm going to add y bar to each side. And write it this way. I think this will be my final form. Okay, so I'll have y hat equals the slope times x plus, in parentheses, I'm going to have a y bar minus the slope times x bar. Okay, so again, the slope we've given. Now the slope I used, I think, a b for the slope. So the slope is b. I'll put that in later. The slope is it was r times sy over sx, and the y-intercept is y bar minus the slope times x bar. Okay. And another fact we get from this point slope form not only gives you the slope, but it also gives you a point on the line. Okay, the x coordinate here in the parentheses and the y coordinate, those have to be on the line. So the point on the line is x bar, y bar. So we're going to call this the mean point. But it's also called the centroid, so I'll do that in parentheses. The centroid is just the center of the distribution. So we're saying that the mean point, x bar, y bar, the mean of x's and the mean of y's, that point has to be on the line that goes through the middle of the data. It totally makes sense. Okay, this mean point is the centroid. It's the center of the data set, the two variable data set. And yeah, this we are saying that the line has to go through that point. So that's the next question here. What point is always on the line of best fit? That's x bar, y bar. Okay. Just one last comment again. The y-intercept is referred to as A. And the slope is B. Okay, and the line of best fit is y hat equals a plus bx. That's how it was originally given in the lesson. All right, so that's everything there. Good Lord. So we've created it. We have to get some meaning out of it now. So there's a little more algebra to do. Not much. Okay, you guys ready? Any questions at this point? We'll do an example, obviously. Okay, so we've got what point on the line of best fit? Always the centroid x bar, y bar, the mean point. We also want to measure total variation of points on the regression line from corresponding points on the mean line. The sum of squared deviations from the regression line is denoted SSR. We just call it sum of squared regression, sum of squares regression. Okay, so the sum of these squared deviations is SSR. It measures variation in Y that's explained by the line of best fit. So let me go back to our original graph. Not that one, this one, okay. The purple deviation that I put in there is the explained part. Okay, we're saying that every point deviates from the mean in this data set. Some of the deviations are explained by the explanatory variable. So remember, X is the variable that's used to predict Y. That's the explanatory variable. X predicts Y, but the language they use is X explains Y. I would rather they call it the predictor variable, but they don't. Nobody does. It's the explanatory variable, so we say that X explains Y, and this deviation, this increase of Y from the mean value of Y's to the line of best fit is the one where we're using the explanatory variable to predict this point on the line of best fit, because the line of best fit is Y equals A plus BX. X is in the equation. It is used to predict or explain Y. So that's why we call this increase the explained increase. Any increase beyond that is unexplained, okay? The explained deviation plus the unexplained deviation add up to the total deviation. Okay, any questions? Okay, so this right here is the total explained deviation. The part where we're using the explanatory variable to predict it. And they want us to simplify it. So as before, this is actually super simple. As before, we have a difference of Y coordinates here. So I think I can just rewrite this as the sum of the standard deviation of Y squared times the difference of their z-scores, which is something we've talked about. So the z-score of Y hat minus the z-score of Y bar. Okay, now we did discuss that the z-score of the mean is always 0. So that z-score of Y bar will be 0. The mean is 0 standard deviations from itself, and that's why its z-score is 0. The z-score of Y hat, that's the line of best fit. So this would be R times the z-score of X. So that's just the definition of the line of best fit, that the z-score of Y hat is R times the z-score of X. So you can rewrite this. I'll factor out that variance of Y from the sum. And what we end up with is, in the parentheses, an R times the z-score of X, and then minus 0. That's going to be squared. The R squared is constant. It can factor out. So you could write this as sy squared times r squared times the sum of the z-scores of x squared. And then we have a tool in our little toolbox for that. We've decided that the sum of the squares of z-scores, any complete set of z-scores, if you square them and add them up, you'll get your sample size -1. So this part here is n minus 1. So in the end, this total is n minus 1 times r squared times sy squared. Okay, so this is the total explained deviation from the mean. The part that we're using the explanatory variable to predict. The predicted deviation, if you like. Now, the total deviation in Y is the difference between a given Y coordinate and the mean. Okay, so that's the deviation you use in the standard deviation. So it's pretty easy to remind ourselves that the standard deviation of Y squared is you add up the deviations of each Y value from the mean, Y bar, you square those, otherwise they add up to 0, and then you divide by the sample size -1, and the square root of that is the standard deviation. But I think you can see that if you multiply both sides of this by n minus 1, this top is this total deviation in Y that we call SST. Okay. So if you take this n minus 1 here and just multiply both sides by it, it comes out on the left side. And so you get that SST is just n minus 1 times the standard deviation of Y squared. So we can just put that down without any work. We can say this is n minus 1 times the standard deviation of Y squared. Okay. Now it says, what's SSR plus SSE? So SSR plus SSE, this is the explained deviation. This is the unexplained deviation. Okay, I'm going to make this a little smaller so I can write the word deviation under this. Okay, well, if you look up, SSR was n minus 1 times r square. Is that SSR? Yeah. R square times sy square. Now, SSE was a little further back to here. This is SSE, the minimum value of SSE. So it was n minus 1. I'm just going to copy that and probably have to shrink it a little bit. So again, that's the unexplained deviation. I'll paste it here and make it smaller. So I think you can see there's some factoring you can do on this. You can factor out the sy squared and the r squared. No, you can't. You can factor out the sy squared and the n minus 1. So I'll underline what I'm factoring out. Except for I made the mistake again. We're factoring out sy squared and n minus 1. So this becomes n minus 1, factoring out the sy squared. And then what remains after you do that is you have an r squared plus a 1 minus r squared. This is just 1. So in the end, you get n minus 1 times sy squared. And if you just look up above, immediately above, that's SST. So these add up to the total deviation. So what we're saying is that if you do the total of the unexplained deviation, sorry, the explained deviation, those are the deviations from the mean to the line of best fit, plus the unexplained deviations from the line of best fit to actual data points, that the explained part plus the unexplained part always adds up to the total deviation, which is used in the standard deviation of Y values, total deviation from the mean. Okay, so the next part is they want us to look at some ratios. Here, they're taking the proportion that's unexplained. Let me circle this with the blue. Okay, so this is the explained proportion of total deviation. And here's the unexplained proportion of total deviation. Okay, what do they add up to? If you think about it, it makes sense. Remember, SSR plus SSE is equal to SST. If you divide everything by SST, okay, what do you get? Well, this first one is the explained proportion. The second one is the unexplained proportion. Okay. This thing is just 1. So we can say then from all that if you do SSR over SST plus SSE over SST, this will be 1. Now it says, what's the value of SSR over SST? Well, SSR over SST, going back, SSR, I'm just copying and pasting what SSR was. And dividing by SST, I'll copy and paste that next. And you see there's some cancellations. This just results in R squared, which was the slope of the line of best fit in the ZX, ZY plane, but now the slope is squared, okay? This is the proportion of total variation in Y that's explained by X, the explanatory variable, using a line of best fit. Wow, I can now say, wow, there's a certain percentage, a proportion can be converted to a percentage. So once I know what R is, I can say, oh, well, if you square that and it comes out to be 90%, then I'm going to say 90% of the variation in Y is due to X. Now, I don't want to make that sound like cause and effect, but I'm going to say that basically the explanatory variable is explaining 90% of the variation in Y. Okay, without using the words cause and effect. So we'll have to be really careful about that. I know I need to stop, but let me get a couple things out of the way because it'll be too hard to start up later. One thing I know, okay, so I just want to make a note here. These are both positive. SSR over SST, we just figured out is R squared. Okay, turns out when you simplify this thing, that comes out to be 1 minus R squared, and you can see it in the, if you just solve for it, you can see it's 1 minus R squared. But the point is that these are positive numbers because they are all sums of squares. And they have to be between 0 and 1 because they add up to 1 here. Okay, so we can say, first of all, that R squared has to be between 0 and 1. Now, R can be negative because it's the slope of a line. Lines go downhill sometimes, especially with negative relationships. So when you square a number between -1 and +1, you get a number between 0 and 1 because squaring it makes it positive. So that is to say that R has to be between -1 and +1. Okay, I think I'm going to stop here. I'll go ahead and answer these. Yeah, we're just going to answer these three. So what do we call R squared? R squared is the coefficient of determination. It's just a term in statistics that's used a lot. It's an important number. And why is it important? Because it determines how good your explanatory variable is at explaining your Y values. Or predicting, if you like the word predict better than explain. I already gave the interpretation for R squared, so I've just copied the answer down from above. It is the total proportion of total variation in Y that is explained by your explanatory variable. So it's just telling you how good your explanatory variable is at predicting Y. Okay. And finally, R gets a name too. R is the correlation coefficient. Okay, so now with the correlation coefficient, we want to start talking a little bit more about what we think R can tell us about the relationship between two variables. So the first thing is, remember SSE stands for the sum of squared errors or residuals. Now, if all the points are on the line of best fit, then the sum of squared residuals will be 0, because if the points are on the line, then there are no residuals. So we can just easily say from this that SSE has to be 0. Okay. Now, don't forget that SSR over SST, that's the explained proportion, plus SSE over SST is the unexplained proportion. And we've said this is going to be 0 if all points are on the line. Okay, so we can say the unexplained proportion is 0 here. Oops, let me clean that. okay, because SSE is 0. And the sum of these is equal to 1. Now, again, the unexplained proportion is 0, so that means SSR over SST is, you're adding 0, so it has to just be 1. And then I just want to remind you that SSR over SST, that's the explained proportion, and it's equal to R squared. So now we know that R squared will be 1 when all the points are on the line of best fit. Okay, so if R squared is 1, then we know that the range of values here is that R has to be plus or minus 1. Okay. And and this is the slope, R is the slope in the ZX, ZY plane. Okay, so if the points are all on an uphill line, then R would have to be 1 because the slope has to be positive. And if the points are on a downhill line, then R has to be negative 1 because the line goes downhill. It has a negative slope. Now, it says, what is the value of R when none of the variability in Y is explained by the line of best fit? Well, I can just take this equation from before and copy this down here. And if none of the explained proportion is, none of the variability is explained, then this explained proportion would be 0. Okay, so that means that R squared will be, which is of course SSR over SST, this would be 0, which means the only value you can square and get 0 is 0, so R has to be 0. Okay, and putting all these ideas together, we know that when R is 1, that there's a positive relationship where all the points are exactly on the line of best fit. And if R is negative 1, then all the points are on the line of best fit, but there's a negative relationship, so the line goes downhill. Okay, when R is 0, we're saying there is no relationship between X and Y, none at all. If it's close to 0, the rule of thumb is between -0.5 and +0.5, that's going to be a weak relationship. Moderate relationships are between -0.8 and -0.5, or +0.5 and +0.8. Those are moderate. And the strong relationships are the ones that are closest to 1 or -1. So R is either bigger than 0.8 or less than -0.8. So that's sort of the rule that we would have. Now I just kind of want to help you visualize this, so I'm going to pop up to the graphs we had at the beginning of the lesson here. And let's just kind of look at these individually. Okay, so with a weak relationship here that looks like it's sort of positive, I think R will be between 0 and 0.5. Okay, that's just our definition of weak. The moderate positive relationship is going to have R between 0.5 and 0.8. Okay, and then the strong relationship will have R between 0.8 and 1. Okay, and of course when R is 1, the points will be exactly on a line. Okay, the negative relationships are similar to this. With a weak negative relationship, your R value is going to be between negative 0.5, and 0. Okay. The moderate negative relationship should be between negative 0.8 and negative 0.5. And the strong relationship should see R between negative 1 and negative 0.8. Okay. Okay, so any questions about that, you guys? So it's just real common. People that work with data and especially in science, they're using R value to sort of judge how strong a relationship is between variables. There's also a version of this discussion for nonlinear. We talk about R squared is the proportion of variation in Y that's explained by X through a line of best fit, but you can also use R squared to do the same proportion for curves. And the computation is kind of the same as the way we described what the original definition of R squared. So R squared occurs whenever, is a measure that's used whenever we fit curves to data points like we're doing.
For a linear relationship, can you remind me what the slope is in the equations that we've got?
Yeah. So I think you've got it here. This is, and I apologize, there's no page numbers here, but couple pages back from where we are. Oh, and I've lost it. You can see here. So that's just like 2 pages back. We're going to compute this. We'll compute all this in a sec.
Okay.
Okay, any questions? Okay.
I think sorry, one other question. If you could just briefly, just to bring it back full circle for me, if you could briefly touch again on the sum of square errors, the sum of square regression, and the sum of square totals, and just how those fit back into the first equation.
Yeah.
Is that too big a question? I just wanted to see it again. You don't have to do the whole spiel. I just wanted to like.
Yeah. Look, no, it's good. It's good. Okay. So you have to remember that every point deviates from the mean. So we talk about how, oh dang, did not mean to touch that. Okay. We talk about how, see this point, right? Let me pick a good color here. So this point here, again, this blue line is the mean of Y values. So this point actually is whatever this is, it's a murder rate. It's really high for this city. And we don't know why. So we're trying to explain it or come up with a rule for predicting it. Okay. And we see, that if you use a line of best fit for all these points, that the line of best fit predicts this height for the murder rate, what I just circled. Now, predicting is just another word for explaining in statistics, unfortunately. So when I say, sorry, you do? Okay, so we see that we have an elevated murder rate that's predicted or explained by the number of guns in this automatic guns in the city, right?
Right.
That's what we call the explained. Now, when I say SSR, it stands for sum of squares regression. So it's the regression line that explains it.
That makes sense. Yeah, it's that.
It does, but it's just, it makes sense, but it's overwhelming, I know. So SSR is the sum of squares explained, or regression, which is the explained part.
Right.
You're looking at you're basically looking at all these deviations from the line. The explained amount is the deviation from the mean to the line of best fit. Okay, just the amount that is explained by the explanatory variable. Okay, so every one of these, you have to compute the explained proportion, square these, if I screwed that one up, square them and add them up for all the points, and that's SSR, the explained part.
Right.
But then we look at the unexplained part. This is the part we're trying to minimize because we want these points to be close to the line. So we're choosing our line to minimize the unexplained part. And if you do the math, and we did the math, I proved that the formula for the line of best fit minimizes the sum of squared errors, which are also called residuals, and they're also called the unexplained deviations, which I'm trying to limit. Okay. So, and of course, the unexplained part occurs with every one of the data points. So I'm squaring those for every point and adding them up, and I get the SSE, which stands for sum of squares error. Again, residual is just another word for error. Unfortunately, there's lots of words for stuff. Okay, so we chose a line of best fit to minimize the sum of squared errors, and that led to a slope and to a y-intercept for the line. We showed that the total explained deviation plus the total unexplained deviation just adds up to the total deviation, which sort of makes sense, but it's actually super complicated that the sums of squares actually add up that way. We learned that the SSR, which is the explained variation, divided by SST, the total variation, is actually just R squared. And that's just totally out of nowhere. There's no way you could have predicted that.
It's just out of the math.
Yeah, it just came from the math. But knowing that R squared is SSR over SST tells us that R squared tells us about the quality of our explanatory variable. Yeah. This is how good it is at explaining the deviations you're seeing in murder rates. So if R squared comes out to 90%, you're saying 90% of these increases or decreases in murder rates are explained or predicted by your explanatory variable. The better it is at explaining things, the more likely the more likely are to think that this explanatory variable is super important, whatever the issue is. As R squared starts to approach 100%, 0.9, 0.99, 99%, right. As it starts to approach 100%, you start to realize that this thing is key. Again, you have to be very careful about cause and effect ideas, but it's hard to not feel there's a cause and effect relationship as R squared starts to approach 1. Right. You can't prove cause and effect without a proper experiment, and nobody's going to do an experiment with guns and murder rates, because you'd have to give you'd have to have a control group, and then another, with squirt guns, and another group with like automatic weapons. So nobody, and then see how many murders there are. So that's not going to happen, right? So you can never, in a statistics context where we rely on data and very rigid standards for what makes cause and effect, you just can't make that in an observational study like this. Yeah. How do you feel?
That makes sense. No, that was what I was hoping for. That was really helpful. Thanks.
Okay. Yeah, and it's hard to not get buried in this discussion, and I'm trying to explain it well, but thanks for the opportunity to do a better job. And
it was it was a lot of parts. I just wanted to see a couple of the parts again.
Yeah, there's a lot of pieces. Yeah, and the tricky part, the part I hate the most is that the abbreviations the letters SSR those letters aren't actually the right acronym. Same with SSE. They can't use I almost feel like they should do SSU for the sum of squares unexplained, and the SSE for sum of squares explained, but E is used for error. So that's confusing. And
Yeah.
I want to say SSR maybe then could be sum of squares residual.
It's interesting because it
but-
does make, once you kind of get those parts, like the idea that there's somewhere buried in there, there's a ratio of sort of this, like, you know, this unexplained and the total deviation from this line. That ratio implies the fit of the data to the line. That like intuitively that part at least makes sense, even if it's not like perfect.
Yeah. Well, and you know,
That's
like I
helpful.
said, it's maybe look through this again. Like I think maybe a second sweep through it might help kind of lock some of the ideas down. Again, it's just a load of information, and I really enjoy the fact that these things can be explained at this level, meaning without a calculus background.
Yeah.
Which most things in statistics are calculus based, but this is one of these things. It's all just algebra, but you know, obviously it's kind of hairy. So, and there's a lot to keep track of. So it took me a long time where I had this boiled down to a place where I thought I could actually explain it in class. But again, to really grasp it, you probably need a couple passes through on this. All right, so I've got this sense of what makes a relationship strong and weak based on this R value, what makes a relationship positive or negative when R is positive or R is negative. And I can actually measure how good my explanatory variable is, right? Using R squared. Okay, how good is that thing? All right, so we do have our FBI data. I think we actually computed these two z-scores here previously, so I'm going to slide back to that page right here. We computed two z-scores when x is 4 and y is 10. So I'm just going to copy those and paste them down here. Okay, and now the reason why we're doing this is just to remind you, we have that R was determined to be the sum of Zx times Zy over n minus 1. That's the formula that minimized the sum of squares error. Okay, that's what we wanted to minimize. That was the whole point. So what you have to do now is go through and just multiply all these. So if you want to help, that would be great. Or just to verify some of this, we're just going to probably do 4 places after the decimal. So put in 4 places, and then if you shout out one, I'll do the first one here, 1.2860. So if I do 4 places on that, I'm going to write 2.4308. Okay, and then maybe someone could just count these or add these up as we go. Okay, so on that one, I got 0.6031.
Yep.
For the third one, I got negative 0.1279.
Awesome. Anybody have the fourth? Uh, 1.0801, 1.1506. So times, so I got 1.2427 or 28.
1.2.
For the next one, I got 0.5484.
Awesome. So 0.1828 on the next one. I got 0.9321 on the next one. And if any of you guys disagrees with any of this, please shout it out.
That's what I'm being.
Thank you. So I got 4848 on the last one. Okay, does anybody have any complaints about this? It might be worth noticing, remember, we're computing R. Just as a reminder, I don't have the graph. Oh, here's a graph. Nice. Okay, so remember, this is an uphill relationship. So R is related to the slope of that line. And it's not the slope, but it's related to it. And remember, R is positive when the points go uphill. Okay. And if you kind of step back, notice how all of these are positive. Now, that's kind of weird. Why did they, oh, and we're expecting R to be positive. So why did they come out positive? It's the reason why R will be positive. Okay. And of course it has to do with these Z-scores. So look at the Z-scores for a second. Notice that the Z-scores tend to either be both positive, which means you've got values that are both above average. So on the graph, those would end up in the upper right if the Z-scores are both positive with both numbers above average. Again, both Z-scores are positive. Here's the exception to the rule. I'll just cross it out because I don't like it. Okay. But in every other case, the Z-scores are either both positive or both negative. If they're both negative, then both numbers are below average. So the point that you're graphing would be in the lower left. So again, both positive in the upper right, both negative in the lower left. You see, if they're both negative, the product will come out positive. If they're both positive, the product will come out positive. These all come out positive when the points go from the lower left to the upper right, which is an uphill line. And so it sort of makes sense how multiplying these Z-scores determines whether the slope is positive or negative. Okay, and we're sort of just looking at that product and averaging it when we compute R. We're dividing by n-1. Remember, when we average sums of squares, there's not really a sum of squares here, but when we average things in statistics, we always divide by degrees of freedom, which I don't even want to address right now. But this, just think of this as the average of the product of the Z-scores. And again, it just totally makes sense. If it's an uphill line, the Z-scores, when you multiply them, will tend to be positive. If it's a downhill line, the product of the Z-scores tends to be negative. And that's why R, the average of those, comes out negative. So that's another way of looking at that. Did anybody add these up?
I think the last one might be off.
Oh, okay.
I got 4752.
Sure, I'm sure I typed something wrong. 8977. 87. I wonder if that's what I did. So 4752, you said?
That's what I got.
Okay, yeah, that's sure that's right. So 4752. So any of you that that added these up, you would want to subtract out what the last one was. I think I'll just pause. Huh?
For the sum at 8.457.
45, like 70.
4571.
Oh, 71. Okay, cool. All right, any questions there? So when we compute R, we'll do this sum, 8.4571 over n minus 1. Though there were 8 pairs, so when you count n, this is 8. It's the number of pairs, so you got to be careful of that. Okay. So here you would do over 7. Okay, so you guys, this is a mistake. That's too bad. Now, just keep in mind, y'all, that this statement right here, we mathematically proved that R has to be between -1 and +1. So I think something's wrong. Probably the total is wrong. So I'm going to erase that. And I think, gosh darn it. This is 9.1.
Oh, I see.
I did the wrong thing.
Oh, I know why. Yeah, it was the total was wrong.
Okay.
I have a new total that may or may not be wrong.
Well, did anybody get something there? Let's see what you got, and then let's see if anybody agrees with this.
Does anybody agree with 6.2872?
I got the same thing, yeah.
Thank you so much. Now that's going to put us in line with what we mathematically know must be true. 6 divided by 7 is going to be less than 1.
I got 7.3. I don't know if that makes any change.
Opinions, anyone?
That's probably rounding because I'm using Desmos.
Yeah, and we're all going to round a little different. Let's go with the 7.3. That's fine. And so divide that by 7. So you should get 0.8982 maybe. Okay, so that's R. Go ahead and square it. Now, I'm going to square the unrounded version. So when you square it before rounding, you get 0.8067. So R squared is 0.8067. So that's 80 point, it's a little bit ridiculous to be this precise. I'll just say it's about 81%. Remember now, R squared is a proportion. I'm checking something real quick. Here, they're just asking for, yeah, okay. This is fine. I'm just going to try and make a little more space because there's more to do in here. So don't write it too big, but we would say that 81% of the variation in the murder rates can be explained by the number of automatic weapons. Again, maybe predicted. If you don't like that word explained, you can use predicted instead. So let me just add that statement in here. 81% of variation in murder rates can be explained by automatic weapons. I should say the number of, I'll write auto weapons using a line of best fit. Okay, any questions there? These interpretations are really hard to get right. It's R squared is the proportion of variation in Y that's explained by X. How? Using a line of best fit. There are other ways to make predictions. I mean, maybe it's not a line, maybe it's a curve, maybe you're using a curve, and people should know that, you know what I mean? I mean, if you're trying to explain how you explain or predict, the value of R squared depends on the model that you're using. So 81% is not bad, but if it was curved, it's possible a curved model would give a better explanation. So how about that? Now we have to do the slope. So the slope, let me switch back to red here. So the slope, it was called B, I think, in the notes. So this is R times SY over SX. Just to, you know, we proved mathematically that it has to be that way. I always like to think of this as, remember, if from algebra, slope is always rise over run. And I always think of the run as sort of the average change in X coordinates. That's the definition of standard deviation, the deviation from the mean. So the average deviation from the mean in X coordinates, that's the run. The rise is related to the average deviation in the Y coordinates, which is the, you know, vertical variable. So it totally makes sense that you're doing the average run, the average rise over the average run. Totally makes sense, except for what's this R doing here? I would say a couple of things. R serves the purpose of giving the slope the proper sign. So remember, when the slope is negative, R is negative. And when the slope is positive, R is positive. So the R is actually applying the correct sign to the slope. The line of best fit is I'll just erase this in a second, but it's Y hat equals A plus BX. If there's no relationship between X and Y, the R always comes out to be basically zero, effectively zero, okay, when there's no relationship. So the slope ends up being effectively zero when there's no relationship between X and Y. B is the slope. If the slope is zero, then the Y, the prediction for Y doesn't use X, because it makes, when the slope is zero, X vanishes from the equation. So now Y is predicted without X. So R is eliminating X from the equation when there's no relationship between X and Y. That's brilliant. That's perfect. That's what we want. It also diminishes having R here, it diminishes the influence of X over Y as R approaches zero. As it should, because the weaker the relationship, the less influence X should have over Y. So it's actually the formula for the slope, very mathematically derived, but it sort of makes sense. Anyway, I have to go back and grab all the statistics we had, so I'm going to jump back here. I think, I'm not sure, here they are. X bar, SX, Y bar, SY. So I'm going to copy all these down to that page. Somewhere I'll squeeze them in. Okay, so this 5 is X bar. The standard deviation of X is the 3.70. Y bar is the 8.25, and standard deviation of Y is this other number. Okay. Okay, so where are we here? R is point, I mean, don't use R squared here, it's R. So 0.8982 times standard deviation of y, 3.6936, over the standard deviation of x, which was 3.7033. Feel free to shout it out. Okay, I don't know if I like what I just got. I guess this is going to be really close to 1 based on the numbers here. Anybody get an answer for that?
I got 8.8958.
Yeah, that's what I got to. And I don't know how much to round it, but I think I'll just go 0.896. It's a little super precise, and it's always weird when you're super precise with statistical data, which is all full of presumption.
Estimation.
Yeah, full of estimations and stuff. But there it is. And then the y-intercept has a formula that we determined to be y bar minus the slope times x bar. Okay, so this will be our y bar was 8.25 minus the slope, which was 0. I'm going to use the unrounded version of the slope, but I'll write 0.896 times x bar, which was 5. And again, not entirely sure how much to round this, but I'll use 3.771. And you might have just a little different value depending on where and when you rounded stuff. Okay, so we got a slope, we've got a y-intercept. Let's go ahead and put the formula down for the line of best fit. That's just the equation of the line. So it's a plus bx. Just a reminder, the slope is b, the y-intercept I didn't write down, but that's a. So I've just put that here in the notes. Okay, so when we write the line of best fit, we mean y hat is a, that's 3.771. Plus b, that's 0.896 times x. Okay, any questions there? Now it says to add this to the scatter plot. So what you want to do is plot the y-intercept. And the mean point just as a reminder, the mean point is the centroid, it's the center of the data set. And we showed that the mean point has to be on the line of best fit, which is awfully convenient because that gives us, between the y-intercept and the mean point, that gives us 2 points that we know are on there. So again, the y-intercept is about 3.7. This doesn't have to be perfect. So 3.7 is about here, like that. I think I'll do it in a different color. So let me see, maybe blue. 3.7 is about here. My mean point's pretty easy. X bar is 5. And Y bar is 8.25, so just go up to about here. Okay, so my X bar, Y bar, I'll point to here. And my Y-intercept. And then that's all you need to draw your line. So on an exam, I'm not sure what I'll do with that, whether I'll have you do it on a scratch paper or just pick the right graph from a multiple choice question, one of those. Okay. So if it was a multiple choice question, you'd try and make sure that the mean point is graphed right and the y-intercept is graphed right. But I haven't thought about that yet. So somehow I want you to be able to graph one of these lines. Okay, super easy. Any questions? That is it. The only thing I will add, we've got 10 minutes before the break, and then we'll do the exam. The only thing I would add would be that in Desmos, let me just go ahead and tell you how to do all this. So in Desmos, you would do a capital X. I'll make a note of that, but just list all the X coordinates of the data set. So they were up above 12, 8, 4, 12, 8, 4, 1, 7, 3, 2, 3. And then the Y coordinates, it doesn't have to be capital on Y. X is just a special variable in Desmos. Can't use the lowercase x. So Y 13, 11, 10, 4. Um, 12, 7, 4, 5. Okay, so that's easy. And then if you do, mean capital X like that, that's X bar. If you do STDEV capital X, that's X bar and SX. The mean of Y is Y bar. Sorry about that. Standard deviation of Y is SY. Kind of obvious. Here's the kicker, the one that you don't know, and that's core, C-O-R-R, big X, comma, Y. That's R. Super easy. So you have to use a capital X everywhere. I'll give you a second on that. I'm gonna pop over to Desmos real quick, and I'll share it with you in a sec. But for the moment, I'm just gonna paste or copy these numbers in my lists. Okay. So I'm just going to I'm going to pop over to Desmos real quick, and feel free to do the same. You got it in your notes either way, so it's not a big deal, but let's just compare what Desmos does to the values we got in our notes. Make sure everything's right. So for X bar, you would do I need this? So mean of X is 5, STDEV of X is 3.70, which I guess is what we used, yeah. Then mean of Y is 8.25, standard deviation of Y is 3.6936, which we got, and then core. So that was, let's do X comma Y. So that's 0.89. We did that by hand. So 8982 which is exactly what we got. So our correlation coefficient after we did tons of rounding to get that number for the correlation coefficient. But our rounding did not damage the answer much. It's pretty good, actually. Okay, so in section 9.1, we learned how to find a line of best fit to fit a line to a collection of XY data points that seem to be sort of linear in form. When the data points are linear, we have formulas for the slope, the Y-intercept, and for a computation that we refer to as R, which is called the correlation coefficient. So actually, I think I'll go back up to the top of 9.1 just to remind you of what the rules we kind of set down. These basically, when R is in different ranges, it tells us about the geometry of the relationship between the two variables that you're looking at. So the closer R is to +1, the closer the data points are to a linear relationship that goes uphill. That is to say, that is X increases, Y tends to increase as well when it goes uphill. Okay, so those are called positive relationships. And when R is close to 1, we call it a strong positive relationship. When R gets close to -1, we get strong negative relationships, which go downhill. So as X increases, Y goes down on those. When R is close to 0, whether it's positive or negative, when R gets close to 0, those are weak relationships or just non-existent relationships between two variables. Okay. Other case that I think I forgot to mention is the non-linear relationship. If it's very non-linear, the more non-linear it is, the more R will be closer to 0. Okay. The place where there's no relationship at all, again, R is close to 0. Okay, so I never hit those. And so we've got this number R, and it's mostly telling us when there are strong relationships that are linear, either positive or negative. Okay, so the next lesson allows us to determine really that case where R, try to distinguish that case where R is approximately 0 from when R is not 0. And it's a hypothesis test. Okay, so we don't do hypothesis tests on statistics from samples. We do hypothesis tests on measures from entire populations. So actually R is called the sample correlation coefficient. There's also a population correlation coefficient, which is the Greek letter for R, which unfortunately looks like a P, but it's actually pronounced rho, and it just sounds like an R in the Greek alphabet. Okay, so let's go ahead and read this. Again, it's section 9.3. In this lesson, we learn a quick hypothesis test for testing for the existence of linear correlation. As a reminder, the sample linear correlation coefficient is R. Again, that's from a sample. We generally use technology to compute R, but the formula, because the formula is unwieldy, this is a hard computation. We did it once, probably won't do it again. And I think if you remember, the last thing we did in Desmos last time was give a formula for computing R. It's just core XY. So Desmos does that, and you'll be able to use that on the final exam. Okay, so you don't have to compute R. Now, again, R is the sample correlation coefficient. There's a population correlation coefficient. It's called rho. That's the Greek R. Unfortunately, it looks like a P, but it's pronounced rho. If rho is 0, then the population of XY data points exhibit no linear correlation. If rho is not 0, then at least some linear correlation exists in the population of XY data pairs. So you're going to basically test the null hypothesis that rho is 0. That means that there is no linear correlation between two variables. Okay, and then the alternative hypothesis just says rho is not 0, which means linear correlation does exist. And let's put it down as some linear correlation exists, and it could be weak. Looks if I can't spell it. Okay. Could be weak, but at least we're saying at least some exists, and not in the sample, but in the population. So you need some pretty strong evidence in your sample to prove something for an entire population. And that's what the hypothesis test does. So at some point, one of the people that were studying this realized that this R statistic, if the population correlation coefficient is 0, that the R statistic can be standardized to follow a T distribution. So let me go ahead and walk you through the process. When we assume the null hypothesis is true, under this assumption, this condition, the mean of R values is 0, and that's just rho from the null hypothesis. And the sample standard error is this formula. Notice you can see there's an n-2 in the denominator, which will be the degrees of freedom for the test. Okay, the standardized value is a student's T statistic. So the test statistic is R minus the mean of R values over the standard error of R values. Okay. So the mean of R values is just rho, which is 0. Okay, and the standard error is this thing. So we can just rewrite the T statistic this way. There's a discussion in the book that explains why there are not n-1, but n-2 degrees of freedom. We've never seen that before. It has to do with the fact that there's 2 different variables that are used to determine R. And with 2 different variables, it's sort of like you're losing 1 degree of freedom for each. That's one way of saying it, but it's also because there are 2 statistics that are used to predict values for Y, which are the slope and the Y-intercept. You actually lose 1 degree of freedom for each one of those is really the reason. So let me go with this. It says this is a 2-tailed test with n-2 degrees of freedom. Because the standard error uses 1 minus R squared, which is SSE over SST, and SSE tends to be too small because we're using 2 sample statistics to compute it, the sample slope and the sample Y-intercept. You lose 1 degree of freedom because of each of those. So it says conduct this hypothesis test using the data on automatic weapons and murder rate that we covered in the last section, and we're going to use a 5% level of significance. Okay, so as I said before, the null hypothesis says that rho is 0. That means there's no linear correlation. Okay, the alternative hypothesis, very simple, is just always going to be rho is not 0, which means linear correlation exists. And this is going to be a two-tailed test. Okay, any questions? We've already checked the conditions. The conditions are bivariate normality, which I'm not going to ask you to look into. But we've kind of looked at it with the scatter plot that we were talking about before in the last section. So our test statistic is a t statistic. As I said before, it's r over the square root of 1 minus r squared divided by n minus 2. Okay, and so we have to go back and figure out what our numbers were from the last lesson. So let's take a quick peek back there. All right, so you can see the R value here is 0.8982 and that N is 8. All right, so we can just real quickly plug those in. Okay, so we'll get 0.8982 over square root 1 minus 0.8982 squared, and that's over n minus 2, so it'll be 8 minus 2, like that. A little ugly. And then I'm going to pop over to Desmos real quick, so let me get that going. Okay, so let me go there. Okay, so it's pretty easy to do. Pretty much Desmos will do everything for you here. So let's see, 0.8982 divided by, let's get the square root going. And then a slash for the fraction, 1 minus 0.8982. Use a little square button down here if you like. And then down in the denominator, it's over 8 minus 2, which is 6. I'll be real formal and put 8 minus 2 down there. And so you can see the statistic is actually kind of huge. So that means that we're claiming that the population correlation coefficient is 0. And it turns out our sample correlation coefficient is 5.005 standard errors above 0, which is pretty strong evidence that the population correlation coefficient is not 0. Okay, it's not proof, but it's really strong evidence. So let me go back to the iPad. Is there any question about that computation? Make sure, when you're putting it in, make sure the whole denominator is inside the square root. So it's real common for people to put the denominator outside of the square root. So that's the most common mistake. So make sure you practice that a few times. The whole fraction should be inside the square root. Another common mistake is people will forget to square the R value inside the square root. Any questions? Okay, so let's go back to the iPad. Okay, so this, hang on, 5.005, I think is what I'll go with. Okay, and now we need a p-value. I'm going to hold off on the critical value this time. So let's get a p-value out of this. Come on, there we go. A little T on here. Of course, the 5.005 is out in right field. If we look at table A3, which has the t-distribution p-values, For degrees of freedom, this time we're doing n-2. So n-2 is going to be 6. And our t statistic, you got to go down to basically 5.0. Got to round this to one place after the decimal. Okay, any questions about this? Let me real quickly grab that table. I don't see it, but I think I've got a copy of this in chapter 7. So I'm going to pop down to the end of chapter 7 here and grab that table. This guy, it's just horrible. Now what I think I'll do is let's draw from 6 degrees of freedom up here. I'll draw a little line down to the very bottom row at 5.0, and you can see there's a number here. Okay, so this is a t statistic of 5.0 with 6 degrees of freedom. Is there any questions there? That's really close to 1. Okay, so 0.9988. So that's this tail. Let me shade that in a little bit. Actually, 0.99 this is always the area to the left. So this this tail is going to be 1 minus that. Anybody did anybody do that? What's the area of that tail?
.0012.
Thank you. 0.0012. Thanks so much. Now, is that the p-value? What do you guys think? Is that our p-value?
Double it.
Gotta double it. Good job. So it's a two-tailed test. So let's see if we can find a little spot here. Two-tail test means that the p-val is 2 times 0.0012. So this is 0.0024. Either way, it's less than 1%. And I think our alpha was 5% on this. 0.05, yeah. So the p-val is 0.0024. That's less than 0.05, which is our alpha. So we get to reject the null hypothesis and support the alternative. Okay, any questions?
Yeah, so you only multiply it by 2 for the two-tail test, right?
Exactly, and those are the ones where the alternative says not equal. You good? So correct. So yeah, so we reject, support the alternative. The alternative is the one that says here that linear correlation exists. So we'll just say the data support that claim. I'll go ahead and put this in context. Linear correlation exists between the, it's kind of wordy and I only have like an inch. of space to write in. Let me see, between the auto weapons numbers and murder rates for cities. I guess they were US cities, so I'll say US cities. Okay. Got it. Does that make sense, you guys? Anybody want to ask about this? And that's it. So that's like the shortest section we do. Super quick, super easy. Now, when you look at the book, you'll see that there's also another hypothesis test in this section for the slope of the line of best fit. But I didn't assign any of those problems, and it's not going to be tested. So, and I'm not covering because we're not supposed to cover that. We could, but we don't have time, so it's not required. All right, so any questions about this? All right, so we're going to wrap it up. That's all there is to it.